Welcome to the massive open online course on Aspen Plus. In today's lecture, we will discuss about the setting up of property environment. Now, this portion will be discussed in detail in the fourth week of this lecture series when we will discuss about the process and property analysis. But today we will have an introductory session. So the first thing that we have to do in setting up of property environment is to select the components or the selection of chemical compounds with which we will do the simulation in Aspen Plus. For that, let us go to the Aspen Plus software. So this is the window where we need to select the components or the chemical compounds. Now each chemical compound or each component that we select have an unique component name and a component ID which the user has to assign. Now this component ID can be anything. One can use C1, C2, C3, etc. or comp1, comp2, comp3, etc. But it is wise to assign a component ID whose name matches with the actual component name, because in this fashion if you write, then in future you may not remember whether component 1 is oxygen or component 3 is nitrogen. It is very difficult to remember in that manner. So the component ID has to be given which matches with the component name to some extent, or its abbreviation sort of. So one thing that we have to remember, the component ID should be not more than 8 letters long. So there is a limitation in the number of alphabet for naming the component ID. But if the component name itself is very short, that is within 8 letters, then you can directly write the component name in place of component ID, and Aspen is smart enough to identify the desired component itself. For instance, if you want to write or if you want to choose water, then you can directly write water in place of component ID, and the moment you enter it, component name water or H2O, that will be taken as it is conventional. Similarly, if you place acetone, which is again within 8 letter, then it will take up as acetone. But suppose you want to work with methyl isobutyl ketone. This is a long name, so you cannot write it in component ID. So the question is, how can we set this methyl isobutyl ketone? For that, we have to use this find button, and it will find the desired component name from its database. So for that, you have to press find, and here there are several search criteria available. For instance, if you say name or alias equals methyl isobutyl ketone and say find now, it will actually look for the methyl isobutyl ketone and it will dig out the actual component that you are looking for and suggest you. What you need to do, you need to choose it and add selected component, then the component ID will be automatically fixed. So here you can change the component ID also, but it might so happen that methyl isobutyl ketone is not your desired component. A derivative of that or some other ketone is the one which you are looking for. So you want to search for a component which has ketone in its name. So name or alias that contains the word ketone. If you say find now, then you will get all the components that have ketone in its name. The first one is cyclohexyl methyl ketone, then isobutyl heptyl ketone, ethyl methyl ketone oxime, amyl methyl ketone, etc. So you have to choose your component from this list. It's a long list of components from which you have to choose. Now the search criteria gives you the option to choose from molecular weight or boiling point. For instance, if you want to find out the components whose boiling point is between 99 and 101 degrees centigrade. So what you can do? You can simply write boiling point from 99 to 101. So it will give you the list of components that's boiling point is between 99 and 100. And you can very well see one of them is water, whose boiling point is 100. And not only water, there are so many other items whose boiling point is between 99 and 101. All of them are listed over here. So you can use the molecular weight also as a search criteria. Anyway, you have inserted methyl isobutyl ketone over here, and this component ID has been automatically chosen by Aspen, but you can rename it as per your choice. For instance, you may say that you want to call it methyl isobutyl ketone, and then methyl isobutyl ketone will be renamed. So this component ID is given by you. Now you may be curious to know these components have been taken from some database, but what are those databases? For that, you have to go over here, Enterprise Database. So just go there and you will find these are the selected data banks from where these components have been searched. And these data banks are searched in this order: PO37 first, and then aqueous, solids, inorganic, APEOS, and NIST TRC. These are the most common data banks, and for all practical purposes, mostly you will get your desired component from them. But in case this is not sufficient, you may look for your desired component from here. For instance, if you want to search your component from polymer, then you just choose polymer and then use this particular button. Polymer will come from here to here. That means this database also is being included within your search criteria. Now let us see what these data banks are. PO37, aqueous, solids, inorganic, APEOS, and NIST TRC. So these are the data banks you just saw in the Aspen Plus software. First one is PO37. It contains the data from Design Institute for Physical Property Data, or DIPPR in abbreviation, and Aspen Tech. So actually it is a primary component data bank in Aspen Plus. The next one is aqueous. It contains pure component parameters for ionic and molecular species in aqueous solution. They are used in simulations containing electrolytes. The solids data bank, they contain pure component parameters for strong electrolytes, salts, and other solids. They are also used for simulations containing electrolytes and solids too. Fourth one is inorganic data bank. It contains thermochemical properties for inorganic components in vapor, liquid, and solid states. They are used for solids, electrolytes, and metallurgy applications. Next one is APEOS. They contain cubic plus association equation of state model developed by Kontogeorgis et al. This is the paper, Industrial Engineering Chemistry Research. It has been published in 1996, and this data bank has built-in pure component and binary parameters, and they are used for modeling processes such as methanol gas cleaning. And finally, NIST TRC data bank. The full form of NIST is National Institute of Standards and Technology. TRC is Thermodynamics Research Center, and they have critically evaluated thermodynamic property data, and it is used for pure compounds with primary focus on organics. Now, once the selection is done, you have to press next, and it will come at setting up of property method. So it is property methods and option. Now, when building a simulation, it is important to ensure that the properties of pure components and mixtures are being estimated appropriately. In fact, selecting the proper method for estimating properties is one of the most important steps that will affect the rest of the simulation. Therefore, it is important to carefully consider the choice of methods to estimate the different properties. In Aspen Plus, the estimation methods are stored in what is called a property method. And a property method is a collection of estimation methods to calculate several thermodynamic and transport properties. The transport properties are like viscosity, density, thermal conductivity, diffusion coefficient, surface tension, etc. And thermodynamic properties are like fugacity, enthalpy, entropy, Gibbs free energy, etc. And in addition, the Aspen Plus stores a large database of interaction parameters that are used with mixing rules to estimate mixer properties. Now, one of the key calculations performed in process simulation is phase equilibrium calculation. The basic principle of several unit operations such as flash tanks, distillation column, extraction, etc., they are all based on multiphase equilibrium. And phase equilibrium is calculated using fugacity. Now the phase equilibrium is calculated using fugacity, which is a measure of tendency of a component I to leave its phase. And the equilibrium is achieved when the fugacity of the component is equal in all phases. Now say the fugacity of a component I in liquid phase is given by phi IL into xi into P, where this is the fugacity coefficient. Xi is definitely the mole fraction of I in liquid phase and P is the pressure. Similarly, fugacity of component I in vapor phase is equal to phi IV into Yi, that is the coefficient of component I in vapor phase, into pressure P. Now at equilibrium, these two are same. That means FIL is equal to FIV. If the fugacities in two phases are same, that means the equilibrium has been achieved. Now at pure state, when there is no other component in the mixture, only component I, then obviously our Xi will be 1. So is Yi. So both in liquid phase and vapor phase, the mole fraction of component will be 1 because it's a pure component. In such cases, the fugacity will be represented by Fi naught, which is equal to phi I naught into P, because Xi is equal to 1 and Yi also equal to 1. And for non-ideal liquid solutions, the fugacity of the components in solution deviates from that of pure component. So if you find the ratio of FIL and FI0, so this is the ratio, you will find FIL is not equal to Fi0, it deviates a lot. So the ratio of them is called the activity, which is equal to phi IL xip by phi I naught P. That is equal to phi IL by phi I naught into xi. And this is called the activity coefficient. This is called the activity coefficient. So all the non-ideal cases are dealt with activity coefficient. Now in general, this activity coefficient is higher than 1. That means the fugacity of a component in solution is greater than fugacity of the pure component. That means the same liquid will have a higher tendency to vaporize when in mixture than in the pure state. And this can be attributed to the increased repulsion between the molecules in the mixture than in pure state. Obviously, in a few cases, the activity coefficient will be lower than 1, indicating that there will be increased attraction between molecules in the solution state and it will yield less tendency to vaporize. In general, there are 4 choices for choosing appropriate property method: ideal model, equation of state model, activity coefficient model, and other models. The ideal model is applicable for a system composed of ideal gases and liquids. As you might know, the ideal gas, it follows the ideal gas law, PV is equal to nRT, and here the fugacity is equal to 1, and an ideal liquid, it has the activity coefficient 1. Now when will you assume ideal behavior of a system? When you have vacuum or low pressure, or when you have a system with very high temperature, and when there is very small interaction or negligible interaction in liquid. Now, interactions are negligible when molecules of similar size and character are mixed together in the liquid phase. In that case, ideal model will be applicable. And the non-ideality, as a general rule of thumb, will appear when you have systems that involve materials such as water, organic acids, amines, alcohols, esters, ketones, aldehydes, ethers, etc. I mean, when you have them, you are necessarily handling polar molecules. And there is a good chance that your system will deviate from ideality. In such situation, you will use either equation of state model or activity coefficient model. Now, in case of gases, you will generally use equation of state model. Equation of state models are PVT models. You might remember from the knowledge in thermodynamics, you have mainly cubic equation of state model and virial equation of state model. A few popular cubic US models are Van der Waals, Redlich-Kwong, Peng-Robinson, and their extensions. You have cubic plus association also. Among virial equation of states, you have virial expansion, Benedict-Webb-Rubin, Lee-Kessler, etc. And usually when you have pressure less than 10 bar, you can use equation of state model. On the other hand, the activity coefficient models can be used for liquids. There are many: NRTL, Wilson, Vandler, Unifac, Uniquark, electrolyte NRTL, etc. You might be knowing NRTL means non-random to liquid model, and this NRTL model is used for polar mixtures. And in these models, the activity coefficient approach is used to calculate the liquid properties, while the vapor phase properties are calculated using an equation of state model. And if you have a supercritical component in the mixture, then you can use Henry's law in activity coefficient model. Finally, the other models, there are still many other property models available, and they are classified as vapor pressure liquid fugacity models, and they found applications in many specific processes. Among these models are API sour model, and it is developed for sour water treatment applications. And two popular models are Chow Cedar model or Grayson Street model. They are applicable for heavy hydrocarbons. There are also Kent Eisenberg model. They are used for amine sweetening units. Here we have a comparative assessment of two major non-ideal cases, that is equation of state model and activity coefficient model. The first one is equation of state model. They are good for vapor phase modeling and liquids of low polarity, and activity coefficient models, they are preferable for liquid phases. Equation of state models are not used generally for non-ideal liquids, but activity coefficient models are good for non-ideal liquid mixtures. They use less number of binary parameters, and for activity coefficient model, binary parameters are required. Here, extrapolation of data is possible, but for activity coefficient model, they are only valid for the given temperature range. Equation of state models, they are good for critical region of pressure and temperature, whereas activity coefficient model, the critical region are to be avoided. Here we have few recommended methods for a few type of systems. For instance, TEG dehydration, the suggested property methods are Peng-Robinson and glycol package. For sour water system, we have sour Peng-Robinson or sour Soave modification of Redlich-Kwong, and so on. Now, even after knowing all of them, you may still need some kind of assistance to choose the appropriate property method, and Aspen has a ready assistant for you that is called method assistant. So here it is called property method selection assistant. If you click on it, it will open up. So this is the property method selection assistant, and you can start by selecting one of these two following options. You can specify the component type or specify the process type. If you go by process type, you can choose either chemical process, whether your process or application has electrolyte, whether it is for environmental application, gas processing, oil and gas, mineral and metallurgical, etc. If you go by component type, it will ask whether it is for chemical system, whether for hydrocarbon, whether it has special system or refrigerant. So for instance, if we have hydrocarbons in the system, then we have hydrocarbon mixtures. Does the mixture contain petroleum assay or pseudo component? You can say yes or no. Suppose we say no, we do not have. Then these are the options that we have: Peng-Robinson, SRK, LK-Plok, etc. For instance, if you choose Peng-Robinson equation of state for it, then by default, the method name will come as Peng-Robinson equation of state. Now you may be curious to know what are the equations that govern that particular method that is operating. So this Peng-Robinson method, you can see the equation of state, it is showing as ESPRSTD. So just go for help and type here ESPRSTD. So here you see ESPRSTD is standard Peng-Robinson method. So this is the standard Peng-Robinson equation for this model. So basically, Aspen Plus is using this model to do the property calculation. And this model has been taken from this journal paper, Peng-Robinson, a new two-constant equation of state, which has been published in Industrial Engineering Chemistry Fundamentals in 1976. This means the source of information or source of modeling is authentic. Aspen Plus is using some authentic source of modeling technique to do all the calculations. So it's quite reliable. Now, in case you are not happy with this standard Peng-Robinson equation of state, rather you want to modify this. So what you need to do is you need to say modify, and you have to enter a new property method name. For instance, you can give a name like my Peng-Robinson, or you say my Peng-Robinson. So that's the name you want to give to that property method, and immediately it will open up some options for you. So you can change the equation of state from Peng-Robinson to something else. You can use Peng-Robinson equation of state with PSRK mixing rule, or Peng-Robinson equation with state with MHV2 mixing rule. Now, if you want to know what is MHVT mixing rule, again you can go there and look for MHV2. Then Aspen will tell you what MHV2 mixing rule is. So just click on that. It is Dahl and Michelson 1990. This is the relationship equivalent to one used by Huron and Vidal. So this is the MHV2 mixing rule that is used in that type of Peng-Robinson extension. And this has been taken from this paper, Dahl and Michelson paper from AICHE journal, published in 1990. Again, an authentic source. So that is how you can change the Peng-Robinson equation of state as per your wish. If you do not want to use the default one, it will give you the options. And here also there are several equations for calculation of liquid molar enthalpy and several equations for liquid molar enthalpy. All these equations you can search in the help file and get relevant information. Anyway, let us not modify it. Let us delete this modification and let us go by the standard Peng-Robinson and see what happens. Now here, usually Aspen Plus does not give the parameters of its own. If you want to know the pure component parameters, you have to choose retrieve parameter. So it will retrieve all the pure component parameters used in the calculation and display them on the parameters and results form. So if you say retrieve parameter and press OK, then you will find them in this form. Let us first see what the parameters are. This is a selected method Peng-Robinson. And these are the property calculation. What is PHI VMX? Let us see. PHI VMX. So if you click on this, it is vapor fugacity coefficient of a component in a mixture. Similarly, PHIV, it is vapor pure component fugacity coefficient. SV and SL, they are vapor and liquid pure component entropy. Similarly, you have notations for Gibbs free energy, molar volume, enthalpy, etc. All of them you can get from help file. Then you have pure components. It is CPI GDP1. It is methods parameters pure component. What is CPI GDP1? Again you go to the help file and you write CPI GDP and check what it is. It is actually general pure component ideal gas heat capacity. Just click on that. You will get CPI GDP, ideal gas heat capacity polynomial, DIPPR 107 or 127. Let us see what is 107, 127. Here it is. DIPPR equation 107. DIPPR ideal gas heat capacity equation 107 by Alley and Lee 1981. So Alley and Lee in 1981, they have published a paper in Fluid Phase Equilibrium on self-consistent equations for calculating the ideal gas heat capacity, enthalpy, entropy. So on that basis, this equation has been taken. Here in this equation, you may find that ideal gas heat capacity is expressed as a polynomial where coefficients C1, C2, C3, C4, C5 are there, and this equation is valid only within this temperature region, which is within C6 and C7. So you go back to the Aspen domain, temperature dependent correlation parameters. Actually, these are the correlation parameters from C1 to C7. So what are C1, C2, C3, C4, C5? The first 5 components are C1, C2, C3, C4 and C5. What about the C6 and C7? They are also there. They are actually temperature. If you put the values of C1 to C5 in this equation, that means when you are talking about acetone, you put C1 is equal to 12.6412, C2 you put 24.1593, C3 you put 670.19, C4 you put 23.4683, and C5 you put 2186.5. Then only thing that you need to do is to put the temperature value. So whatever is the temperature value you put over here, the temperature unit is C. So the moment you put the value of temperature T, the entire equation is defined. You will get the value of Cp. That means the ideal gas heat capacity of acetone at that particular temperature. And this particular equation is valid from C6 to C7, 0 to 1226.85. That means this is in temperature unit. So this particular equation is valid between 0 degree centigrade to 1226.85 degree centigrade. So the range of temperature within which this equation is valid, that is also given. Same is there for water and methyl isobutyl ketone. Similarly, you will get other things like thermal conductivity, viscosity, etc. Then go to binary interaction. Now you might remember that equation of state requires very less number of binary parameters. Whereas activity coefficient models, they use lot of binary parameters. You can see this from this result. Peng-Robinson equation, it is an equation of state model. It does not have any binary interaction parameter. Instead, if you use say NRTL method, suppose you use NRTL method, then the binary interaction parameters are available. For that you have to again run this equation and all the binary interaction parameters are now available. So acetone water, component I, component J. So the binary interaction parameters are there. For acetone water, acetone methyl isobutyl ketone and water methyl isobutyl ketone. For each pair you will have the binary interaction parameters. And if you want to see the results, here you will find the pure component results. So the freezing point of water, you know, this is the freezing point. It is 0 degree centigrade. Unit is C. So e to the power minus 14. So this is actually the calculated or computed based on the correlations they have found. The freezing point of water is nearly 0, and that is right actually. Freezing point of acetone is minus 94.7. Similarly, you will have other parameters also when they are pure. Here you will have DCPLS. Again, you can look for the value what is DCPLS. It is difference between liquid and solid heat capacity at the triple point. DG form, DGFORM, it is ideal gas gives free energy of formation at 298.15 Kelvin. So wherever you have some doubt, you can just click on this help button and get the appropriate help information. So that's how we use the property method, and we will learn about this property method in detail in our 4th week lectures of this lecture series. Thank you.